So we're going to look at the test for halides, and the first test we're going to look at is the use of silver nitrate, okay, aqueous silver nitrate, followed by ammonia, okay, followed by ammonia, okay. Aqueous ammonia, we're going to be using dilute aqueous ammonia as well as concentrated aqueous ammonia. So in the first step, what we do is, let's say we had a solution of a halide, right? So we had halides are obviously the anions of the halogens. So like if you had a solution of chloride, bromide, or iodide, okay. So in the first step, what you would do is, if you had a solution of a halide, such as let's say for example sodium iodide or sodium chloride, you would first react that with silver nitrate aqueous. Okay, so you would add silver nitrate or mix it with silver nitrate aqueous. Okay, and what you would see is, you would see the formation of a precipitate. All right, so here what happens is that silver ions, okay, combine with the halide ions to form a precipitate. Okay, so obviously the silver ions and the halide ions are in their aqueous form, right? So you're going to take a soluble halide, and you're also going a soluble halide salt, and you're going to have obviously silver nitrate, which is also soluble. But what happens is that silver ions and halide ions combine to form a precipitate, right? So over here, precipitation is the first step, right? So if when we add silver nitrate aqueous, what we get is precipitation. This is the ionic equation for that precipitation reaction, all right? But this is the general equation. And now we're going to look at each of these halides individually, right? So for example, right, if silver ions reacted with chloride ions, okay, if silver ions reacted with chloride ions, we would get a white precipitate, okay, of silver chloride. You get a white precipitate of silver chloride. Okay, so this is a white precipitate. Similarly with bromide ions, okay, silver and bromide combine together to form silver bromide. Okay, that's AgBr solid. Okay, and this is a cream precipitate, sort of like an off-white color. And then lastly, we have silver ions reacting with iodide ions, right, to form a yellow precipitate, okay, of silver iodide. Okay, so we form a yellow precipitate of silver iodide, okay, yellow. Now, if you look at the colors of these precipitates, right, if you look at the colors of these precipitates, or what these precipitates look like, okay, here we have silver chloride, which is a white precipitate, silver bromide, which is a green precipitate or an off-white precipitate, and silver iodide, which is a sort of a very pale yellow precipitate, right? But just by looking at these, it's very difficult to actually identify which precipitate you have. So for example, you might get silver chloride, but we might have slight impurities, which makes it look like silver bromide. Similarly, you might get a silver iodide that sort of looks very similar to silver bromide. They both have a fairly faint color, right? A faint yellow color, is just that silver bromide is slightly lighter than silver iodide. So it's hard to distinguish between these precipitates just by looking at the color, okay, which is why we follow this. Once we form the precipitate, okay, in the second step, what we do is we add aqueous ammonia, okay. So when we add aqueous ammonia, okay, we're going to use dilute as well as concentrated aqueous ammonia to test for which halide is present. Okay, so for example, if we had silver chloride present, okay, silver chloride will dissolve, okay, it will dissolve completely. It dissolves completely in dilute aqueous ammonia. Okay, it dissolves completely in dilute aqueous ammonia. Silver bromide, on the other hand, silver bromide does not dissolve in dilute ammonia. It doesn't dissolve completely in dilute ammonia. Okay, it only dissolves partially. It only dissolves partially in dilute aqueous ammonia. Okay, dissolves partially in dilute aqueous ammonia. Okay, sometimes you'll see it being referred to as does not dissolve. Okay, but it does dissolve very partially in dilute aqueous ammonia. However, it completely dissolves. Okay, it dissolves completely in concentrated aqueous ammonia solution. Okay. So if you have a high concentration of ammonia in the solution, if you have concentrated ammonia, then it will dissolve silver bromide. Obviously, concentrated ammonia will dissolve both silver chloride and silver bromide. But for silver chloride, we don't need concentrate. It will dissolve in dilute. Okay. For silver bromide, it won't dissolve completely in dilute, but it will in concentrated. Okay. So we first test with dilute. If it dissolves completely in dilute, we know that it's silver chloride. If it doesn't dissolve in dilute, only dissolves partially in dilute, then we use concentrated ammonia. If it dissolves completely in concentrated aqueous ammonia, then it's silver bromide. Okay. Whereas silver iodide does not dissolve in concentrated or in dilute aqueous ammonia. It does not dissolve. Okay. Yes. Does not dissolve in dilute. Okay, and concentrated aqueous ammonia. Okay, it won't dissolve completely in either of these cases. So if it dissolves in dilute aqueous ammonia, we know it's silver chloride. If it doesn't dissolve in dilute or dissolves partially in dilute, but it does dissolve in concentrated aqueous ammonia, then we know it's silver bromide. Okay, and then if it doesn't dissolve in either dilute or concentrated aqueous ammonia, then we know it's silver iodide. Now the other test for halides that we have is the reaction of the halides with concentrated sulfuric acid. Okay, reactions with concentrated sulfuric acid. Okay, so we can use sulfuric acid to test for the presence of halides. So we're first going to look at the reaction of concentrated sulfuric acid with fluoride, right, and chloride. You have very similar reactions in both cases. Okay, so let's say for example I have something like potassium fluoride, okay, and I react it with concentrated sulfuric acid, right, so I react it with H2SO4, okay, and what we get here is the sulfuric acid simply behaves as a proton donor or as an acid, right, and we end up making KHSO4. Okay, this is the hydrogen sulfate ion, HSO4 minus. Okay, one of the protons is donated, right, and we also make HF. Okay, so what you're going to observe in this reaction are white fumes of HF. So you can say that the observation in this reaction is that we're going to observe white steamy fumes or white misty fumes. Okay, you have a similar reaction with chloride. So for example, if I had, let's say, sodium chloride, it will react with sulfuric acid. Okay, it will react with sulfuric acid to form sodium hydrogen sulfate, okay, and HCl. Okay, again, what you're going to observe is that again, it's HCl is forming in aqueous solution. Okay, but you're also going to see fumes of HCl evolving from the solution. Okay, just like HF. So again, you're going to see white misty fumes. Okay, evolving. So this reaction can be described as an acid-base reaction. Okay, these reactions are acid-base reactions. We won't call this a neutralization reaction. We call this an acid-base reaction here because if you look at the sulfuric acid, it's behaving as an acid, right? It's donating a proton, it's donating an H plus, and the halides are acting as bases, right? They're accepting the proton. Okay, so you would characterize this as an acid-base reaction because you have a proton donor in sulfuric acid and you have a proton acceptor in the halides, but not as a neutralization reaction. So in these reactions, sulfuric acid, okay, sulfuric acid is behaving, right, as an acid, right? It's a proton donor, right? Okay, it is a proton donor. And we can clearly see that sulfuric acid, despite being an oxidizing agent, doesn't oxidize fluoride or chloride. And that's because fluoride and chloride are relatively weak reducing agents, right? Because down the group, the reducing strength increases, okay? So instead of behaving as an oxidizing agent, it only behaves as an acid, but not an oxidizing agent. And the halides simply behave as bases, but they don't behave as reducing agents in this reaction. What we can say is that sulfuric acid is not a strong enough oxidizing agent, okay, to oxidize fluoride and chloride. Alternatively, we can say that fluoride and chloride, right, are, yes, are not strong enough a reducing agent to reduce sulfuric acid, okay. Are not strong enough reducing agents, okay, to reduce sulfuric acid. Now, in some cases, this reaction will also be written as, this reaction will also be written like this, okay, where you have potassium fluoride reacting with sulfuric acid to form something like potassium sulfate and HF, okay. So they'll usually accept both, okay, but we're going to be using this equation, okay. This is the more widely accepted equation for this reaction, the first one, okay. So we're not going to, instead of writing potassium sulfate, we're going to write potassium hydrogen sulfate in this case. So now let's look at the reactions of concentrated sulfuric acid with bromide ions and chloride ions, okay. So now if you look at the reaction with bromide, the first stage of the reaction is the same, okay. So what will happen is that in the first stage, if you have something like, let's say, sodium bromide, it will react with sulfuric acid, okay. We're going to have an acid-base reaction where sulfuric acid donates a proton, so we get sodium hydrogen sulfate and HBr, okay. And what we're going to observe is, again, we're going to observe white fumes. So first HBr is produced, okay, and then once HBr is produced, okay, the HBr reacts with sulfuric acid in a redox reaction, okay. The HBr reacts with sulfuric acid in a redox reaction, and we end up making bromine, okay, we end up making bromine, sulfur dioxide, and H2O. Now the reason this happens is because bromide is a stronger reducing agent than chloride and fluoride, so it's able to reduce sulfuric acid. It undergoes oxidation more easily, so we can also say that sulfuric acid is able to oxidize bromide ions. Okay, and the balanced equation for this is we have 2HBr, okay, and 2H2O. So over here we can see that the oxidation number of bromine, the oxidation number of bromine is going from -1 to 0, right? And the oxidation number of sulfur is going from +6 to +4. The oxidation number of sulfur is going from +6 to +4, right? In sulfate or sulfuric acid, the oxidation number of sulfur is +6, and sulfur dioxide, the oxidation number of sulfur is +4. Okay, so sulfuric acid is the oxidizing agent, okay? It undergoes reduction, and the bromide ions are the reducing agent. They undergo oxidation. So another observation that we make here is that we're going to see orange or brown fumes of, okay, brown fumes of bromine. Now we look at the equation for the overall process. Okay, the equation for the overall process is the following. Okay, what we have here is, that sodium bromide, okay, reacts with, okay, sodium bromide reacts with sulfuric acid. Okay, sodium bromide reacts with sulfuric acid to form sodium hydrogen sulfate, okay, bromine, sulfur dioxide, and H2O, and H2O. So here we have 2 NaBr, 3 H2SO4, okay, and we have 2 NaHSO4 and 2 H2O. So the equations for the individual processes that are taking place are these equations, okay. We have two separate reactions taking place. First, sodium bromide reacts with sulfuric acid, okay, where sulfuric acid is behaving as an acid, and then the HBr that is produced reacts with sulfuric acid in a redox reaction. Here sulfuric acid is behaving as an oxidizing agent, and the halide is behaving as a reducing agent, okay. So these are the These are the two separate equations for each of the reactions that are taking place, and this is just the equation for the overall process. Okay, so what we have then over here is that sulfuric acid, okay, sulfuric acid is behaving as an acid, okay, as well as an oxidizing agent. So the first reaction that we have is an acid-base reaction, okay, and the second reaction that we have is a redox reaction, right? The first reaction that we have is an acid-base reaction, right? And then the second reaction that we have is a redox reaction. So we can say here that sulfuric acid, okay, is a strong enough oxidizing agent, okay, strong enough oxidizing agent to oxidize bromide, okay. And because bromide undergoes oxidation more readily than chloride or fluoride, okay, in this case we can say that bromide is a strong enough reducing agent to reduce sulfuric acid, okay, strong enough reducing agent to reduce sulfuric acid. So this overall process is basically two separate types of reactions taking place, right? We have the acid-base reaction taking place and the redox reaction taking place. So now we're going to look at the reaction of iodide with concentrated sulfuric acid, okay? So let's say, for example, we had potassium iodide, okay, and we reacted it with sulfuric acid, okay. Again, right, when we reacted with sulfuric acid, what we get is an acid-base reaction, right, in which again sulfuric acid is behaving as an acid, right? It's a proton donor. So we get potassium hydrogen sulfate, okay, KHSO4, and we get HI, okay. And again, we're going to observe white fumes. But now we also know that iodide is an even stronger reducing agent than bromide, okay. So again, we're going to have redox reactions with sulfuric acid, okay. Iodide will be able to reduce sulfuric acid, all right. So multiple reactions take place in this process, okay. So we have multiple redox reactions take place, okay. Okay, so one way in which hydrogen iodide can react is in a very similar way to hydrogen bromide, okay. So HI can react with H2SO4 to form iodine, sulfur dioxide, and H2O. And the observation that we have here is that we see a purple vapor of iodine, okay. We see purple vapor of iodine. Okay. However, because iodide is a much stronger reducing agent than bromide, okay, hydrogen iodide can also reduce sulfur further, okay. It can reduce sulfur further than just to sulfur dioxide, okay. It can reduce sulfuric acid further. Because it can reduce sulfuric acid further, okay, we also get the formation of elemental sulfur. So hydrogen iodide can also react with sulfuric acid to form, okay, to form iodine again, okay, to form iodine again, plus sulfur plus H2O. And the observation that we see here is we see the purple vapor forming, but at the same time we also see a yellow solid form, okay. We also see a yellow solid form, that's sulfur. We have 6HI and 4H2O, okay, and 3I2. Now hydrogen iodide can reduce sulfur even further, okay. It can reduce sulfuric acid even further, okay. So hydrogen iodide can react with sulfuric acid, okay. It can react with sulfuric acid to form, okay, iodine, okay, hydrogen sulfide, and H2O. And here we have 8 hydrogen iodides reacting with one sulfuric acid. Okay, so for every 1 mole of sulfuric acid, you're going to have 8 moles of hydrogen iodide reacting. Okay, and you're going to have 4I2 and 4H2O. So over here again, okay, sulfuric acid first behaves as an acid, right? So the first reaction we've written here is an acid-base reaction. Okay, the first reaction is an acid-base reaction. However, because iodide is such a strong reducing agent, okay, once we form that hydrogen iodide, iodide can reduce sulfuric acid to sulfur dioxide. Here the oxidation number of sulfur decreases from +6 to +4, right? But again, because iodide is such a strong reducing agent, it can also reduce sulfuric acid, right, to form sulfur. Okay, so the oxidation number of sulfur decreases from +6 to 0, right? Because here obviously sulfur is in its elemental form, right? So the oxidation number is 0, right? And then we also see that when hydrogen sulfide is produced, the oxidation number of sulfur decreases from +6 in sulfuric acid to -2 in hydrogen sulfide. Okay, so iodide ions can reduce sulfuric acid all the way from sulfuric acid to hydrogen sulfide. Okay, this is the lowest oxidation number of sulfur. Okay, but all of these things are happening in this, all of these reactions are taking place, okay, between sulfuric acid and hydrogen iodide. So the observations that you get in this entire process, that you're going to see purple vapor form, you're going to see yellow solid of sulfur form, and you're also going to observe white fumes of hydrogen iodide. Okay, all three are observations for the reaction between iodide and sulfuric acid. One thing that you can label as an observation, but it's not really an observation that we make because we're supposed to avoid it, is the smell of hydrogen sulfide, right? Hydrogen sulfide is a gas that has a rotten egg smell. Okay, so if hydrogen sulfide is produced, okay, it has a very strong rotten smell. However, it's very toxic, so you're not supposed to smell it. Okay, you're supposed to avoid places where you have hydrogen sulfide. Okay, so the key observations here are that you're going to see white fumes of hydrogen iodide, you're going to see purple vapor of iodine, and you're going to see the formation of a yellow solid. Okay, so these three are all redox processes. Okay, now this equation here is the one that you should definitely know. Okay, because this is the greatest extent of reduction of sulfuric acid, is when we form hydrogen sulfide from sulfuric acid. So over here, if you were asked to just write the equation for the reaction between hydrogen iodide and sulfuric acid, okay, we would show the greatest extent of reduction, which would be the formation of hydrogen sulfide. However, all of these processes are also, and as far as the overall process is concerned, if we were to construct an equation for the overall process, right, for the formation of hydrogen sulfide, right, from potassium iodide, okay, what we have is we have this acid-base reaction and this redox reaction that we're looking at. Okay, this acid-base reaction and this redox reaction, and the equation that we get is we have 8 Ki, okay, reacting with 9 H2SO4. Okay, 8 Ki reacting with 9 H2SO4 to form 4I2. Okay, then we have H2S, we have 8 KHSO4, right, 8 KHSO4, so we have KHSO4, and then we have H2. We have 4H2. Okay, again, this equation only shows the acid-base reaction that's taking place here, as well as the redox reaction that results in the formation of hydrogen sulfide. Okay, so this is the overall equation for this acid-base reaction and this redox process. Okay, this is obtained by adding this equation to this equation. Okay. Okay, so again over here I've just shown the overall equation for the formation of the most reduced form of sulfur. Okay, iodide ions will reduce sulfuric acid all the way from sulfuric acid to hydrogen sulfide. This will be the most reduced form of sulfur. But you can be asked to construct equations, okay, showing the formation of other products formed in this process as well. Okay, and there will be enough information provided to you in the question to let you know what reactants you have and what products are forming. So then with iodide we can say that sulfuric acid, okay, sulfuric acid is behaving as an acid as well as a sulfuric acid behaves as an acid and an oxidizing agent with, okay, as an acid and an oxidizing agent with the iodide ions. Right, what we can say is that it is a strong enough oxidizing agent, okay, it is a strong enough oxidizing agent to oxidize iodide ions, strong enough oxidizing agent to oxidize iodide ions, okay. Similarly, we can say that iodide ions are strong enough reducing agents, right? So iodide is a strong enough reducing agent, okay, to reduce sulfuric acid. So we know that the reducing strength of the halides increases down the group, right? And that is obvious in their reactions with concentrated sulfuric acid, okay? Fluoride and bromide won't be able to reduce sulfuric acid. There'll only be an acid-base reaction, no redox reaction, right? With bromide, you will have an acid-base reaction as well as a redox reaction. So bromide is a reducing agent and sulfuric acid is the oxidizing agent, okay? With iodide, again, you'll have acid-base reaction as well as a redox reaction. Iodide will again be the reducing agent, okay, but it will be a much stronger reducing agent than bromide. So you'll have a much greater extent of reduction of sulfuric acid, and sulfuric acid will be the oxidizing agent.